Talk about Chapter 9. It's in Pipe Welding Procedures, page 136 in your text, and horizontal pipe welding. Now, before I talk about this chapter, I want to explain that your book, back in Chapter 5, likes to present vertical welding first. It talks about going uphill. Because it's the hardest one, they like to throw that at you first. In our program, we like to teach the 2G first, get everybody used to welding with pipe, prepping pipe, and all of that. So that's why I'm going to cover Chapter 9 first in here. So we're going to talk about horizontal pipe welding, 2G position. Horizontal pipe. And if you'll remember from our last lecture, that means it is the vertical fixed position. That is, if you're going to make a 2G weld, that means the pipe is running up and down, vertically fixed, and your weld is across this way. That's where that name comes from. Okay, reading from page 136. I'm in the middle. Let's see, I'm just above that photograph in the second paragraph, where I'm going to start. And it says, the molten metal in the puddle constantly tends to drip downward. When you're making that weld, gravity's going to try to pull it down. The edge of the upper pipe, when in a fluid state, also flows downward, causing undercuts and the development of a very large keyhole when welding the root bead. When you're welding that root bead, if you don't use a slight up angle on your electrode, gravity is going to pull down on the inside of the pipe. And those of you that have done some of this know what I'm talking about. You'll get internal undercut on the upper side of the bead. So you want to have a slight up angle on this electrode as you're coming through, so that the force of the arc coming off the end of the welding electrode helps to counteract that tendency. You want to establish your keyhole, just like in pipe welding or plate welding. You want to make sure that you've got a keyhole here, so that here's your bead, and that keyhole is eating into the bevel, like so. If you don't see that keyhole and you don't hear that sound of ham and egg or bacon and eggs frying in the frying pan, you're not getting penetration. So you want to watch that keyhole as you're coming across on there. Dropping down below the photograph here, it reads, the width of each bead or layer of weld metal should not exceed approximately 3 times the diameter of the electrode in order to avoid excessive weaving. Well, when I teach you how to do this, let's say this is the edge of your bevel. You can't weave it too wide. If you weave it too wide, you're going to get overlap like this. Overlap is defined as weld metal deposited in the joint that has not fused to the base metal. That's overlap. So usually I'll only allow weaving on the hot pass, on the second bead. If you've got your first bead in like this, and your root bead is in, then you can use the W technique here to put that first pass in. After that, everything goes to stringer beads. If you try to weave beyond that, then you're going to get this type of overlap. Proper term is overlap. You'll hear people call it cold rope or cold lap. Those are improper terms. Proper term is overlap, as defined by the American Welding Society. Your book continues to say, for this reason, more layers of weld metal are required when welding pipes in the horizontal position. After the root bead and second pass are welded, the following beads are deposited in the manner of a bricklayer laying bricks in constructing a wall. A foundation layer is first welded in place, and following layers are welded on top of it. Instead of having a single bead, the cover layer is built up in this fashion using several beads. Now, just as a heads up to you, the things I've already talked about, there's going to be 3 questions on these things that I've already talked about in those first couple of paragraphs. So this is what they're talking about in the manner of a bricklayer. A weld is made one layer at a time, and each layer consists of beads. And you want the face of each layer to be flat. So when you're depositing these beads, make sure that they're going in there nice and flat. If you'll turn the page to 138, top of the page, middle of that first paragraph, it says, usually slightly less current is used when the weld is a horizontal weld in the 2G position than when pipe is in the 5G position. Too much current can cause serious trouble in welding by making the molten metal in the puddle on the upper edge of the weld difficult to control. If you've got too much current, it can cause problems as you're trying to come across here. Not only, well, in my view, from my experience in welding, the primary problem is internal undercut. I've failed more people on pipe tests for internal undercut than almost anything else. And that's simply because they'll either use the wrong rod angle or they'll have too high a current. Either of those two things can really cause you problems. You could have the correct current but be moving too slow and have that same problem. Or one other thing that can cause you problems, you've got everything else right. You got yourself a nice little land there and you've taken all your time to get that all fixed up, but then you're shoving the electrode in too far. You've got the electrode shoved in so far that you've gone through half of your land already. You've got it shoved so far into that keyhole, and then the force of the arc is blasting the rest of that land out of there. And you can get an internal undercut by actually shoving that electrode in too far. So those are some of the things that can cause internal undercut you want to be careful of. The electrode angle for welding the root bead in the horizontal 2G position is shown in figure 9.3. This angle should be maintained when welding around the entire pipe. The side angle of the electrode should not deviate more than 5 degrees from the horizontal plane. Any further deviation can result in undercutting, which in turn can cause cracking, especially in heavy wall pipe. Now, if you look at figure 9.3, it says that it wants you to have a 90-degree angle. Well, in my view, and in my experience, that can cause undercut here. So I would prefer that you have a slight up angle. Now this is one instance in which the author of this text and I disagree. I would like to see a little up angle. He says use it straight in. Use them both. See which one works for you. But if you have problems with internal undercut, use that slight angle. If you look at the figure 9.4, it says arc length, and look at the relationship of the rod to the land. He's got a little bit of a land here, and that welding electrode is held just off the land. You see, so this keeps you from blowing out that land and getting internal undercut. The author suggests holding it off 1/32 of an inch, and that's just about right. A lot of times I'll say just go ahead and rest it right on the outside face of the land. If you can hold it on the outside face of the land, you usually get good penetration. It's just when you try to shove it in too far that you can have internal undercut. Now, does everybody know what a land is? I've described that. It's properly called your root face, but a shorthand term for it is land. Okay, last paragraph on page 138. And incidentally, there's only one question comes off this page. For welding the root bead, the correct arc length is about 1/32 of an inch above the root face. That's what I just spoke about, which is shorter than that used to weld the root bead in the 5G position. The weld should not be started against a tack weld. Usually it is started about 2 inches away from the tack weld. So this gentleman, and this is a good point. I agree with him here. When you've got your pipe, and you've got your tack in here, let's see. You've got your tack in here like so. What you're going to do is you're going to strike your arc out in here and then drop back to pick this up. But your text will go on to say that you should feather these tacks down to a fine edge, just as the way we've been showing you. And the reason for that, of course, is so that when you have your tack like this, after you've ground your tacks, you're going to start your arc back up here, And then as you progress out this way towards the end of the tack, you want that arc, that welding arc, to melt through this before you reach the end of the tack so that you have a good consistent tie-in. It blends in well with that tack. We'll talk about coming into one of these tacks here in a little bit. Again, reading from your text, it says, the arc should be struck in the joint ahead of the weld. Why do you strike it in the joint? You guys know why you strike it in the joint? Why do you have to strike it in the joint and not out here? Huh?
So you don't leave chicken scratches? Or?
Chicken scratches, yeah. What's the proper name for chicken scratches?
Flag?
No, arc strikes. Arc strikes. And what's the danger of arc strikes?
Weakens the joint or weakens the metal.
It does weaken the metal through what they call micro fissures. Little tiny cracks that you can't hardly see with the naked eye, but every time your arc strikes the surface of that steel, you're changing the physical properties of that steel and causing a what's called a martensite structure, which is highly abrasion resistant, but it's hardened, and so it can cause cracking in here. And many companies, if you do this, if you get these chicken scratches, these arc strikes on steel, well, in 1104 pipeline welding, it's a cutout. If you get an arc strike across the surface of the steel, it's a cutout. You have more than two of those cutouts, they're going to tell you to roll your stuff up and hit the road. Same thing in boiler making, in pipe welding, the pipe fitters union. It's just a sign of bad technique. So you always want to strike your arc in the joint a couple of inches ahead of where you want to be and drop back. And it doesn't even have to be a couple of inches. The author says a couple of inches, but if you're just even a half an inch out in front and then drop back, that's fine too. Okay? Okay, as usual, a long arc is maintained until it has stabilized and the gaseous shield is formed. If you notice, when you first strike the arc, of course, it's a little unstable. So you want to allow it to long arc a little bit, and just a little bit, until the arc is stabilized. Then you move in close and back to where you want to pick up the bead from. Then it's shortened to a 32nd of an inch above the root face and held in place until the keyhole is formed. When this occurs, the weld is started using the whipping procedure. Now this guy prefers to use a whip, which is fine. A whip is fine. But if you read your entire text there, he's talking about a whip that is out back, out back, out back, out back, not more than 1.5 diameters of the welding electrode. So it's more of an oscillation, which is fine. When you use this oscillation, what you're doing is you're preheating that land as you're going along so that you get better penetration. And that's a perfectly fine technique. I prefer, and I teach, just striking the arc, dropping back, tying into all those surfaces, and then using a consistent drag motion with it. That works just as well. If you're having problems getting penetration, if you're not getting enough penetration, then you can use this whipping technique to preheat and give you a little bit better penetration. But again, either technique will work for you, and I'd be happy to show you both as we go through this. In fact, this is why we teach you whipping back in Weld 1755 and 1760. But it's not way out and way back. It's not that. It's just a slight oscillation as you go through this thing. The big thing here is to make sure you have that keyhole and you're hearing that sound of penetration. Dropping down to the second paragraph from the bottom, it says the object of whipping is, of course, to control the pool of molten metal and prevent it from sagging. The length of stroke should be about 1 or 2 electrode diameters. So you're not going out very far at all. Dropping down a little bit further, it says, while welding the root bead, attention must be paid to the keyhole and the molten metal. If the keyhole shows signs of increasing, the speed of welding should be increased slightly and the electrode angle decreased slightly. Why would he want to decrease the electrode angle? All right, here's something else that you all may not know. Let's look down on your pipe. We're looking down on the pipe from above. And you've got your tack here, you got your tack here, you got your tack here, you got your tack here. I'm going to weld this quarter of the pipe. Well, when I'm welding this quarter of the pipe, I have my welding electrode pointed back into the puddle like this, this puddle is going to get hotter and I'm going to get deeper penetration as I come across. If that keyhole starts to get a little bit big on me, then I can decrease the amount of heat in that puddle by pointing the welding electrode away from it. Now I'm not going to get as much penetration and I'm not putting as much heat into the weld puddle. This is why he says you can decrease that and it will really help you control it. The other thing you can do is you can go to that whip. If that keyhole starts to get too big on you, if it starts to open up, what you can do here is start whipping and whip it straight out and straight back. Don't try to chase a keyhole from side to side. If you try to chase a keyhole from side to side, you're simply going to concentrate that heat and that keyhole is going to get bigger. But you want to whip it out and back, pause, whip it out and back, pause, and that will allow that keyhole to close up for you. And try this because it really does work. And usually when I'm welding pipe, that's about the only time I'll use a whipping motion. That and when I'm coming into a tack. When I'm coming into a heavy tack, you can use the whipping motion to preheat that tack before you get there, and that will help you tie into it too.
And that's with 60-10, right?
Yes, that's with 60-10. Now there is a page in this chapter that deals with depositing a root pass with 70-18, but we're not going to discuss that in this class. That's a special technique that some of these mines out here, some of these trona mines use. But that's not typically something we would do. Okay. Off of page 138, you've got one question coming. Off of page 139, you have one question coming. Let me finish this sentence. By increasing the speed of welding, the heat is not retained in one position as long as when welding at a slower rate, and the heat buildup in the weld is decreased somewhat. Slightly decreasing the electrode angle allows some of the heat from the arc to escape through the root opening during whipping. To control the keyhole, the welder should maintain a short arc length at all times. By not using the prescribed shorter arc length, the keyhole may become enlarged. You got to remember the characteristics of your arc. It actually comes off of there at an angle. So if you're in close, you're not going to be heating a very large area. But if you long arc it, then you're going to be heating a larger area. So it's going to be that keyhole is going to be getting hotter all around you, all in front of you. And it's going to cause it to get a little too hot and therefore increase on you. So you want to maintain a short arc at all times. And once you've got that 60-10 going, it's really, really tough to stick it. You know, and that's why I say shove it in there, because too many people allow it to long arc. And if you long arc it, instead of penetrating that land, let's see, how do I want to describe this? Okay. No, that's not how I want to do it. Okay. If you long arc it, instead of penetrating inside of this thing, like we want to do, what you're going to do is you're going to bridge it. You're going to bridge it and get lack of penetration. If you long arc it, it's going to bridge. So you want to keep that shoved in there nice and tight so that you're getting through to the other side. And again, the key is still listening for that sound of penetration. If you can hear that, you're getting through. Dropping down to the middle of page 140, stopping and restarting. I'm going to read from the second paragraph in this subject. It says, when welding the root bead, the arc is struck in the weld joint a ½ inch in back of the keyhole. So this guy's telling us now just a second ago he was telling us to strike out in front, but he was referring to your hot pass and such. When you're striking your keyhole, when you've got your root pass in there, well, I teach a ¼ inch. I haven't shown you anything in plate yet, but in plate and also in pipe, I teach that you should strike it back here, and you come right out to the edge. And the whole idea here is you pause right on the edge of that weld, whether it's not your tack, but on a restart, you're going to pause right on the edge of that weld. And the idea is to sit there and let the heat from the arc melt where you left off. And once that has melted off, then think of that welding electrode as a hot knife slicing through butter. And this is your weld bead. And you want to take that and you want to slice right through the end of it. if you can slice right through the end of the tip of that weld where you left off, get down in this keyhole with your electrode, and then pause for a moment, give everything a chance to tie in, and then take off, you'll get a good tie-in. You'll get a good tie-in. And there's actually two ways that we do these root passes. One is on your tacks where we're going to blend them, grind them like this and come out slowly. That's one way. That's when we're nice and prepped up. But if you're welding across there and your tack's over here and you don't have enough welding rod to reach it, what are you supposed to do? Paul, what are we supposed to do there? If we can't make that tie-in, what do we do with our electrode?
Yeah, take it out and start over again.
After we
Punch through.
Exactly right. We punch it through. You punch it through and it'll open up your keyhole. When you open up your keyhole, that's when you use this technique. If you don't stop and regrind this, and a lot of times out in the field you won't. A lot of times if you're doing a production weld, you won't stop and feather the end of that off. Here in the class, that's fine. Feather it off, that's great. You know, there's not a problem with that. And if you have time to do it, feather it off. But out in the field, a lot of times you don't have time. You just got to grab another rod. Your helper's standing there handing you another rod. Then you use this technique where you strike back here 1/4 of an inch, remelt it, get down to that keyhole, and go on. So there's two techniques there that you have to use. Questions so far? Okay. Let's go on. Now, there's two questions. There's two questions from the beginning of that subject to the bottom of that page. So make a note of that. You're going to have two questions coming out of those 3 paragraphs. Now, making a tie-in. The biggest problem that people have in pipe welding, and I see it every year, is coming into a tack and going out of a tack. If you've got your tack here, and this is what a tack usually looks like. This is your pipe fitted together, and it's going on around making its curve. So, and of course you'll have another tack over here and another tack over here. When we tack our pipe up, we always tack it at the cardinal points. What would be 12, 6, 3, and 9. So you got your tack right here. And of course we feathered every one of these tacks so they look like this. Well, the trick is to tie into each tack coming out and going in. Well, coming out, it's not too bad. If you've feathered it properly like this and you've got that big old keyhole, just use the technique of starting up here, come out slowly, and burn through that tack before you reach the end, and it's going to be nice and smooth. If, however, you haven't feathered it properly, if your tack instead looks like this on the ends, and you come out and you're moving too fast, and this especially happens on the bottom of pipe in the 5G position, what happens is your weld picks up and you have a little void right here where you have lack of fusion. It didn't tie in. It didn't blend properly. These are called toenails, and you'll get them going out of a tack, and you'll get them coming into a tack. Toenails. So the best solution for those is to go ahead and feather those tacks properly, and then come out slowly, burn through the tack before you reach the end. You get a good tie-in. But coming into a tack now is, in my view, tougher than going out of a tack. And so let's read here, making a tie-in. When welding toward the keyhole, a weld can be continued at a normal speed of welding using the whipping procedure. When the keyhole begins to close, now here he's talking about, say we were coming this way in our progression, which is fine. You may go that way. But if you're coming into a keyhole, is what he's talking about right now. The whipping motion is carried over the end of the bead to which the tie-in is being made. So if I've worked with you individually in the welding booth, I've told you not to stop once the sound of penetration stops. When you're tying into a tack, keep welding. We keep welding until the trailing edge of the puddle ties in, not just the leading edge. We want that trailing edge to tie in. By using that whipping technique, we're preheating this so that we get a better tie-in and a better blending. And again, if it's feathered, it'll make a really nice tie-in. Okay, the welder must watch the molten metal as it fills the space between the two beads. And then when this space is neatly filled with metal, the arc must be quenched by sudden movement of the electrode away from the weld. So you're coming along there and you're whipping, and that's a good idea when you're closing a bead. Like I said before, I like to use a drag or a push when I'm putting in a root bead. But when I'm coming up to a tie-in, especially coming into one, use that whipping motion to you just kind of step forward and back, step forward and back, step forward and back to preheat that tack. And then once that ties in, then you can go ahead and just flick it out. And that's what he means by quenching. You get away from it quickly. All right. Next paragraph here reads, the procedure for welding toward the heavy end of a bead is very similar. This is what he's referring to as the heavy end of the bead. The end of the bead without a keyhole in it. This allows time for the heavy end of the weld to get hot enough to obtain good fusion with the oncoming molten metal. As soon as the bead that is being deposited gets close enough, the whipping motion should be directed toward the heavy end of the bead to which the tie-in is being made. It may even be advisable to pause momentarily a few times when the arc is over the heavy end of the bead. So again, it's just like when we were coming out of that and we heated the end of a weld about 1/4 of an inch back and the hot knife through butter technique. Same thing here. He's actually saying that you may even want to pause over the end of that tack a little bit as you're whipping to preheat it enough to get that good tie-in. And those are all good techniques, but the key is still proper preparation of the tack before you ever start. If you feather that down, if you feather those tacks down to a fine razor edge, you're not going to have any problem with these toenails. And like I've said before, I've failed probably, well, most welders I've failed on visual has been internal undercut. But the second most thing are these tie-ins on their tacks, because they just don't get proper tie-ins. Always remember that the tack becomes part of the weld. And you've got to have thorough fusion between the tack and the weld bead. Okay. Am I overkill? Am I explaining stuff clear enough? Okay. All right, pour fit up. Pour fit ups are our next subject here. And this section actually talks about if you've got too wide a root opening, how do you fill it? Well, he talks about depositing nuggets, and I've used this technique before myself. But remember, when you're out there in the field, you're going to be working to a welding procedure specification, a WPS. That WPS is going to specify what that root opening should be. And usually it'll say something like, say, 1/8 of an inch plus or minus 1/16. Anything beyond those limits, then the joint fit up isn't acceptable and you're in violation of the WPS, and therefore by code you can't weld it. You got to refit it. But we're going to cover this because it's good for non-code stuff, and frankly I've seen it used in code stuff when people are in a hurry. You know, they gotta button something up so they can get back online. It seems like when you get near the end of a job and that deadline's approaching, the enforcement of the code gets a little lax, and not on the inspector's part, but on the contractor's part, on the customer's part. Well, no, they'll just take some shortcuts. But anyway, what he says here is to use say we've got, well, let's see, that's what is that, 5/32? 3/16? Let's say we're a little bit over. I know my math is a little off. So what he's saying, what he describes here in the text is to go ahead and build a nugget. That is, put a little weld bead on there, like so. Just build up one face until you can bridge it, okay? And then once you've bridged it, go ahead and make your weld using what he calls a U technique. And he describes his U technique as more of an L, like this. And in that manner, you can bridge this. Now, I've used this technique in gas metal arc welding. I can't say that I've ever used this technique in shielded metal arc welding. And this book is about shielded metal arc welding, so it must work on that as well. And then once you've gotten that root bead deposited, then you go back and you grind all this stuff out of there, and you put good root metal in it. But that's the technique he's describing there. But you got to remember, first things first, what's the WPS say? And is that root opening beyond what's allowed by the WPS? And I would not, if I'm a crafts person out there and I'm faced with that dilemma, and I know that it's beyond what's acceptable, I would not go ahead and weld it without first seeking prior approval from my supervisor, because you don't want to get run off the job because you did what you thought was right. You know, pass the buck because you know it's wrong. Over on page 143, continuing with bad fit-ups, what happens if it's too narrow? Say this is too tight, and this is a common thing. If the root opening is too narrow, what are you going to do? Well, your text says that when the root opening is too narrow or is closed entirely, the root bead can be welded by using a higher current setting and a normal arc length. This will increase the heat input into the weld and the penetration. The puddle must not be allowed to become too large or it will sag. To prevent sagging, it may be necessary to resort to the whipping procedure. So if it's too narrow, it's not going to take you long to realize it's too narrow. Stop, crank up your amperage. Another thing that you can do, and I see pipe welders, pipeliners do this a lot. If they've got it like this, and these guys, they only use like a 1/16 of an inch land. If this is too narrow and they're not getting through, they do what's called softening. They'll take a grinder and they'll grind right down into here. And they'll remove some of that bevel. That's what they term softening. They'll go around it with a grinder, they'll thin that out, and then they could still use their normal welding current and blow through that. So those are a couple of techniques that you can use. Then the other things, and I'm really glad he mentions this, it's going back to our land, our root face reinforcement right here, root face. If this is too thick, and Paul, you know this especially, and you'll come to find out about it. On this pipe, this is not a bad example. Right here, this part of the land is about a 1/16 of an inch thick. But over here on the opposite side, this is about 3/16 of an inch thick. So if you were to fit this pipe up and you set your heat to where it's just right for this 1/16 of an inch, and you got good penetration, you're welding on around it, you get to this part where it's 3/16, there's too much meat there, you're not going to be able to penetrate it. So here you have good penetration, here you won't have any penetration. What do you do in those instances? Well, to begin with, you got to remember that your joint fit up is an essential variable. You want to make sure it's right. So prior to doing any welding, you're going to make sure that land is consistent all the way across there, just like in plate. You want to make sure that land is consistent all the way across. But if you have too narrow a root, our text says a narrow root face can be welded by reducing the current setting and by using the U-weave to weld the bead. When the root face is too wide, the current setting should be increased slightly. If the puddle tends to sag, it may be necessary to resort to the whipping procedure or to use the U-weave. So this is what your author is recommending on that. Personally, if I'm making a weld and I see that I'm not getting penetration because that land is too thick, I'll use the softening technique, or I'll turn up my amperage, or maybe a combination of both. Okay? We're not going to, well, I should mention this. I wasn't going to cover root bead with low hydrogen electrodes, but I will tell you this. One question comes out of that section. Okay, one question comes out of root bead with low hydrogen electrodes. Flip the page to page 144, the second pass. So all this time we've been talking about, well, briefly at the start of our discussion we talked about the root bead and the hot pass, but now we're going to go into the second pass in a little more detail. And it says, I'm reading from the top of page 145. Instead of pointing toward the upper pipe, the electrode should be held in a horizontal position with an electrode angle of 5 to 10 degrees. The current setting should be higher than that used in 5G. A slanted looped weave, shown in figure 9.9, is used to weld the second layer. This weave resembles a handwritten letter I that leans slightly toward the left. The electrode should be advanced about 1/2 of its diameter for each weave. The weave I like to use is the W technique. If you got your root pass in there, what you can do is I actually like to use a bit of an up angle, and you pause on the upper side here to allow some of the welding electrode to melt, and whether it's plate in the horizontal position or pipe, you're going to deposit some weld metal here, and then you're going to come down, back up, and pause. Come down, back up, and pause. Just like this. This is the W technique, and it will deposit that second layer, and it will make it flat if you use it properly. And this is what I like to teach. The other way you can do it is to put in 2 stringer beads. Instead of using the W technique, if the joint is wide enough, you can put 1 bead down here and another bead up there and put in just 2 stringer beads. More often than not, you'll probably have to use the W technique, depending on what pipe you're using. Schedule 40 pipe, you could use this, and it's actually just a slight oscillation. If it's Schedule 80 pipe, you could probably use the 2 stringer beads. Dropping down to the middle of the page, it says, the width of the bead for the second pass is controlled by observing the edges of the root bead. The molten metal should be allowed to penetrate into the beveled surfaces of both pipe to obtain good fusion and to prevent undercutting. For heavy wall pipe, 3/8 of an inch or larger, the width of each layer of weld metal should not exceed 3 times the diameter of the electrode when welding in the horizontal position. So if you're going to use this W technique, and I have seen some people use it to weld things all the way out, don't go any wider than 3 times the electrode when you're doing it in the horizontal position. The problem with this, and the reason I don't like to use this beyond the second pass, is because if you do, it's going to sag on the top, and it's going to sag here, and you're going to get overlap on the bottom of it. So once you've gotten past your root pass, your second pass, go to stringer beads, because you don't have any problem about it sagging or catching undercut or catching overlap if you're using stringer beads. And incidentally, off of page 145, there are 2 questions coming. Turning the page, it says, using this weave on heavy wall pipe will result in incomplete fusion of the weld metal with the base metal and the metal in the adjacent weld beads. One other difficulty occurs when using this technique. When the electrode is completely out of the puddle, the weld metal is left exposed to the atmosphere, causing oxidation and porosity. This occurs very readily in high alloy steel pipe, and for this reason, a large weave should be avoided and never used to weld such pipe. So again, if you're going to use it, my recommendation to you is to only use it on your second pass and not beyond that. Third and fourth passes, jump into page 143. Oh, incidentally, there's going to be one question that comes off of 146. On page 147, it says, when welding the third pass, care must be taken to prevent the third pass from being deposited close to the upper pipe. An open crevice must be left in which the fourth pass can be deposited. The reason for this, you've got your root pass in here, and then our second pass is like this. The third pass needs to be deposited like so, leaving some space there. The key thing when welding a joint, no matter what the joint configuration is to tie into all the surfaces. You want to tie into that bevel, you want to tie into that second pass, and then you want to tie in to your third pass. Well, to tie into that second pass, you've got to be able to reach it with your welded electrode. If you can't, if you put this pass too high, you could get lack of fusion right up there at the toe of that. When we go to bend it, it could crack on you, or if we were to X-ray it, we could see the lack of fusion, depending on whether or not the X-ray source was correctly oriented. So, an open crevice must be left in which the fourth pass can be deposited, so that you tie into all the surfaces. That's a key phrase you should remember throughout your welding career. If this crevice is too small or too narrow, it may not be possible to weld a sound fourth pass, as it may lack good fusion and have slag inclusions trapped in the weld. I'm turning the page now. When the third and fourth passes are being deposited, the arc should be kept away from the extreme edges of the pipe bevel, as they are easily burnt away by the intense heat of the arc, resulting in an undercut. Another reason you shouldn't, you want to stay away from these nice little beveled edges until you're ready to cap it, because if you want to leave those as your road sign, as your marker, as your guide when you go to cap those off. Okay. Dropping down, 5th, 6th, and 7th passes. These are your cover passes, and incidentally, he calls these 5th, 6th, and 7th. He calls them 3rd and 4th. But it's really up to the welder and the joint configuration. It might take 12 passes to make one of these welds instead of 5 or 6 or 7. Okay, it says, I'm reading from the second paragraph here. It says the cover passes must be neat in appearance, and they should form a crown or reinforcement of about 1/8 of an inch. Anything over 1/8 of an inch is not acceptable. And incidentally, there is a question that comes off of this paragraph. As before, they are deposited by building from the bottom up. The 5th pass is deposited over the 3rd pass and so forth, so that when you're done, it looks just like that. Okay? It says this pass should extend beyond the 3rd pass about 1 electrode diameter at the lower edge of the pipe. Although not desirable, a certain amount of drooping of this weld will probably be unavoidable. I disagree. That can be avoided. What he's saying here is we've got this sucker all filled, and he's saying that when you put that first bead on for your cap, you're going to get overlap here, and you can't avoid it. You can't avoid it. There's no reason for overlap, and overlap is a defect. And if you're welding a code, this will get called on you. If you make that weld and you leave that little edge right there, there's not a reason in the world it shouldn't just blend in just like so. If you overfill this bead, if you overfill it to where that filler pass comes all the way out to the edge, or you burn that edge up, then you are likely to get this overlap. But if when you fill that root joint, whether it's plate or pipe, and you fill it to within about the thickness of a clear lens from being flush, you won't get that. Okay? All right. Turn the page to 150. We're still on the same subject here, and I'm reading from the first paragraph. It says, many times when preparing edges of heavy wall pipe by flame cutting, the fabricator either forgets or ignores preheating the heavy wall pipe of low and medium alloy pipe. Without preheating, the effects of the alloy on high carbon pipe leads to a hardening of the bevel surface. This surface may then develop microcracks or microfissures due to the very fast cooling rate. The effect is similar to other materials that are welded without preheating, though they should be preheated. With some pipe alloys, the heat-affected zone may not be affected if no preheat is used. Yet, it is important to use a grinder and remove the oxide and the surface metal approximately to 1/1400ths of an inch deep to avoid hardening of the surface bevel. So if he's used a beveler, pipe beveler, or even a milling machine, he could affect the heat-affected zone. It could cause hardening in alloy pipes. So you want to prep that pipe with grinding before you do any welding on it. And there is a question comes out of that paragraph. Dropping down another paragraph, it says high carbon pipe materials, as well as those of alloy type with a propensity to harden, should be preheated to avoid cracking of those short tack welds and to avoid shrinkage stress cracking. Before starting, the welder should examine both edges of the tacks to be certain there is no initial porosity or tear at the edges where the tack was discontinued. That's all I'm going to read there. Basically, if you're using a high carbon steel or an alloy steel that has a propensity for cracking, you got to preheat it. And again, if that's the case, read your WPS. Your WPS will tell you if you're supposed to preheat it, and make sure you do preheat it. If the welding inspector comes by and sees you welding on something and there's not a torch within 50 feet of you, you're going to get your ass reamed out for that.
You're the one that does that, right?
You bet. Or get your money. Usually if I see it more than twice, that's when I say get your money. Going to the next page. First paragraph says, when preheating is applied initially on a hardenable steel, the interpass temperature is much higher. It should be maintained during welding to prevent a hardened microstructure and a weld with a high residual stress, which can lead to cracking. Preheating and the interpass temperature during welding slow down heat dissipation from the weld and the surrounding area, thus providing both an allowance for hydrogen diffusion and a weld with the required toughness. So if you have a high carbon steel or an alloy steel that has a propensity for hardening and you have to preheat it, usually it'll have an interpass temperature that will say 550 maximum, and sometimes it will give you a minimum, say 400 degrees minimum interpass temperature, meaning that while it's being welded, and you've got a lot of this out at the power plant, while it's being welded, between the shift change or lunch or whatever, the temperature of that can never drop below 400. And the reason for this is as you're adding all that metal in there, hydrogen, atmospheric air can get in there and nestle between the grain boundaries of the metal. Well, if you maintain this heat, then that allows that stuff to percolate out, just like the fizz in a soda pop. That hydrogen will percolate out of the weld. Of course, you can't see it, but it will. It will diffuse out of that weld and therefore be less susceptible to cracking. If you were to quench it or walk away from it on a really cold day, and it cools off too much, well, you've trapped that stuff in there. You've trapped it between the grain boundaries, and those molecules of hydrogen are too large to nestle between those grain boundaries. The result is it puts stress on those grain boundaries, and that's what leads to the cracking. Huh? Is that clear as mud? Okay. Let's see. There are two questions that come off of that page, and I've just covered them both. Turning the page to 152, it says, parts of this text have described the effects of carbon and other alloying elements on steel. The discussion of carbon steel has considered steel containing as much as 1/4% carbon. That's a medium carbon steel. Above this range, there is little doubt that precaution must be taken to plan a welding procedure that avoids cracks, brittleness, and hardening. If you get more than 25%, and actually most texts will tell you more than 0.4% carbon, that's considered a high carbon steel. Anything above, now think about that. If you had 100 pennies, if you had a piece of pipe and let 100 pennies represent that piece of pipe, that would be less than 1/2 of 1 penny amount of carbon mixed in that mixture. Well, that's not very much, but that's enough to give it such strength that it's susceptible to cracking. So, and it's not just the carbon content. You can put in alloying elements, and those alloying elements could have the same effect. And for that reason, if you look at the bottom of that page, they have what's called a CE formula, or carbon equivalency. All right, somebody's going to yell at me because I spelled that wrong. Carbon equivalency. And you notice our numbers, I'm going to write this on the board. our numbers are percent carbon plus however much magnesium is in there divided by 6, plus however much nickel is in there divided by 20, plus however much chrome is in there divided by 10, plus however much Cl1. I'm afraid I don't know off the top of my head what that is. Divided by 40, plus, your molybdenum, or moly, MO, divided by 50, plus vanadium, divided by 10. If you do these calculations, you'll come up with a carbon equivalency. And if that carbon equivalency is 40 or above, then it's got to be preheated. Interpass temperature's got to be watched. You may have to post-weld heat treat it. And in your text, when you come to take the test off this chapter, there is a question in there that gives these percentages, and you're asked to calculate what that carbon equivalency will be. So when you're ready to take the test, bring a calculator so that you can do that. Let's see. Top of the next page it says, when the carbon equivalency exceeds 0.40, cracking is possible. Welding most high carbon pipe material and those that incorporate alloying elements in the low alloy and medium steel requires controlling the cooling rate. As welding progresses, welds cool at a rate known as the critical cooling rate, increasing the hardness of the heat affected zone. The structure known as martensite is known for its hardness, poor ductility, toughness, and short range stress, eventually leading to cold cracking. So you want to make sure that the cooling rate is controlled as well. The application of supplementary heat to the joint before welding is an important part of the welding procedure. It alleviates the temperature, it elevates the temperature of the pipe immediately before welding and is called preheating. Preheating lowers the cooling rate as the welding arc moves along. For a given set of welding conditions, such as current setting, speed of travel, and material thickness, the cooling rate will be faster for a weld made without preheating than with preheating. So it's going to draw off that heat a little bit better, give you better properties, less possibility of cracking, less residual stress in there. And you got to remember that it may not crack immediately, and usually it doesn't. But those residual stresses remain in that weld after you've walked away, and it could be a year later that the cracks will appear, especially if it's under vibratory stress. If it's sitting there and it's hooked up to a piece of equipment that's constantly vibrating, it's just like taking a piece of wire, and if you just flex a piece of wire back and forth time and time again, pretty soon it's going to break in two. Same thing applies to your cracking. Okay, therefore, the slow drop in temperature allows for transformation by diffusion to a final structure called pearlite instead of the hardened structure called martensite, which is more likely to form if the joint was not preheated. This treatment in the welding operation is due to a number of reasons. The principal ones being the following. To avoid cracking in the heat-affected zone, to increase the toughness and improve the ability to withstand adverse conditions, to reduce residual stress and internal stress from shrinkage, to minimize shrinkage and distortion, to prevent cooling at elevated temperatures that would allow a ductile structure, to slow down the cooling rate in order to give time for hydrogen to diffuse from the hot weld. There's 3 questions come off of this page, but let me read this last paragraph, and definitely I believe one of those questions is going to be give me 2 or 3 reasons why we have to do this type of heat treating. But the last paragraph reads, when a welding procedure is stipulated as requiring preheating, it is complemented by a stated interpass temperature as well. When working with an alloy steel, the interpass temperature has an effect on grain refinement of the weld metal. The time between beads affects the extent to which the grain size is defined. Depositing weld metal immediately after another may result in no grain refinement of the weld metal. Allowing the previous bead to cool to room temperature before depositing the next bead will yield less grain refinement than depositing the next while the previous one is still hot, but below the critical range. The significance of refining successive weld beads is reflected in the notch toughness impact value. When doing 1104 tests, they want you to record the length of time between one bead and the next, just for that reason, especially on a procedure test. Not on a performance test, but on a procedure test, so that they can get an idea what the notch toughness of the weldment would be. And under ASME B31.3, they have a paragraph in there that talks about interrupted welding. If you're making a weld and you're recording all of that, and you're recording the time between each pass, if you go away for lunch and then come back, there are certain conditions and requirements you have to meet before you can start welding on that again, so that the notch toughness can be maintained. And generally, they require that you reheat that pipe back up to a certain temperature and maintain that temperature for a while before you start a resumption of welding. Okay. Last page, actually there's two more pages. Alloy steel in high temperature services. Welding at high temperatures demands that the weldment be made of alloy steel because of two property limitations of iron and carbon steel, which grow weaker as temperature rises. These are a decrease in strength and an increase in corrosion and oxidation. Chromium and molybdenum, or molychrome, steel, also known as chrome moly, were originally developed for elevated temperature services. They have been extensively used in power plants, pressure vessels, heat exchangers, and other applications where very high temperatures are involved. Molychrome steel is used because it maintains strength at high temperatures and also resists creep, which means that it does not stretch or deform under load after long periods of use with high pressure and temperatures. And that's especially critical in power plants. As some of you may know, there's inside a boiler, inside a power plant, there are pendants, what they call pendants. And a pendant is nothing more than like a curtain with a bunch of 2-inch or various size tubes on it, welding tubes, boiler tubes. And they might have weld here and a weld here and a weld here. And this might be, say, 347 stainless steel, and this section here might be chrome moly, and this section up here might be what they call T11, which would be an 11% chrome. But because chrome moly resists creep, the weight of that hanging down there inside a boiler where there's an open flame and you've got pressure inside this and steam up to 2,000 pounds and more, the chrome moly steel helps to keep it from stretching and failing under those stresses. And that's the purpose of the chrome moly. Get those characteristics in there. I would read that entire page because that's a pretty important page. And there are a couple of questions that come out that will be on the test on that page there. Your test consists of 25 questions. I've covered them all, and I've tried to give you a heads up of where they are. So read the text. If you have any questions, anything you're not clear about, get with me, and I'll be happy to go over it with you. Any questions? Okay, thank you.